You guys see the screen?
Yep.
Okay. Second. One second, sorry. All right, we're all here. I'm here. You're here. Everybody's here. Okay, so we were talking about kind of integration and how you account for the number of hydrogens in the molecule with NMR, and we talked about this simple molecule. This is pretty easy, right? We had 2 to 2 to 3. 2 protons, and 3 protons. And when we looked at the integration, we were able to say, oh, well, that's kind of like 2 to 2 to 3, right? Now, the arrangement of the peaks, we're not quite there yet. We will be there today, but for now, it's just the area under the curve, like the little red line, I guess. And you should be able to see, yeah, that this, if this is 2, well, then this is 2. And then this is probably 3, right? It's a little larger, so you can kind of make that estimation. And do you remember the other thing I said about what kind of peaks usually come around 1? Like multiples of how many? Usually maybe 3, right? So if you see something around 1, you might think, oh, it's a CH3. It's like a methyl group, right? And that's definitely the case. This is a methyl group here, yeah. And which methyl group is it? Oh, the only methyl group that's in the molecule. Okay. All right. So cool. That's kind of where we were, and let's keep going. And okay, yeah, ignore the multiplet patterns. That's what I mean by, like, you see this, it looks like it's like a triplet. It's like peak, 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 and all these little mini peaks. That's something else. We'll get to that shortly. Let's not worry about that this second. And the other thing is, you know, where the peaks are. The one thing you should know, though, that, like I said, was that like a chlorine, like this chlorine will drag the CH2 down to the left, and that's definitely the case. So this CH2 is way down here at 3.5, right? Okay, I'll give you just another word for that, and we'll see that word again shortly. So if the CH2 connected to the chlorine is to the left, I call it downfield. So this left region is called the downfield region, okay? What do you think the right side is going to be called? What's the opposite of down? Up. So the right side is going to be upfield. Right side's upfield, left side's downfield. And we're going to see that over and over. So left, downfield, okay? All right, assignment of the peaks will be made easier in a minute or two. Okay. What about, okay, if I have a molecule like C5H11Br, okay, how many protons are there? There's 11, right? So let's just look at this one more example. Now this is a different molecule, and we're not even going to show the structure this time. I make it even scarier for you, right? Okay, 11. So how, without even considering the structure, how can we account for 11 protons? And there should be there's 11. So like if I consider, like, how many peaks are there? Well, there's the left one, Is that downfield or upfield? It's downfield, right? And then it looks like I have like a little mini peak and then kind of a larger peak and then this kind of really big one. How can I come up with 11 protons? That's the question. How can I come up with 11 protons? All right. How can I do it? Well, maybe we should think first, what's over at 1? It might be a CH3 or it could be 2 CH3s, right? It could be 3, it could be 6, it could be 9. Well, if it's 9, that's not going to make sense, right? That would be leave us 11 minus 9 is 2. So that these would have to be 2. That's impossible. But it could be 6, right? It could be 6. 2 times 3 is 6. Okay, so what's 11 minus 6 is 5. And then you could see, well, maybe if this is 6, maybe this is 2 to 1 to 2, right? 2 to 1 to 2 is 5, right? And 6. That adds up to 11. That's kind of the strategy. Do you get it? So yeah, I mean, like this one looks like a half one. Yeah, that's like a single. That's a CH. That's a CH. I'm thinking CH2, CH, CH2, right? That's 5. And then 2 CH3s, right? Without even considering the structure. We're not even considering the structure yet. We're just looking at the red curve and how do we add up to 11, right? Somebody said you can subtract the tallest peak against the smallest peak to derive the amount of protons on each stage. That's kind of true, you know, it just depends. And the big thing is just know what am I trying to achieve? I'm trying to achieve 11, right? It's got to come up, add up to 11. If I got something at 1, well, that helps because it's 3s, right? 3, 6, 9, what, right? So if this is 6, well, then the rest of it makes sense, right? Okay, we're going to see more examples of this. We're just getting started, but yeah, in this case, 2 to 1 to 2, 5, plus 6 is 11, right? Okay, so we're not even going to show the structure, right? We'll know that we can do the structure later. That'll be easy. Where would the BR be? Yeah, great question. Where would the BR be? Well, we know the BR is electronegative, and things that are electronegative are downfield. So it's probably going to be on the CH2, right? It's going to be CH2 with a BR on it, right? So that's a great question. We'll do more of that in a second. Just give me a second, all right? Yeah, the BR is probably on this CH2 over here. Okay. All right, but that's the integration and how it relates to 11 protons. All right. Useful hint, signals that come around 1 or 2 are often multiples of 3. So it could be 3, 6, 9, right? How do you know if it's 3, 6, or 9? It kind of depends on everything else you got, right? That's how we figure out it's 6. Okay, fun word to say 20 times really rapidly. Diamagnetic anisotropy. Diamagnetic anisotropy. It's gonna hurt. Try it. So what this means in normal words is why protons absorb at different frequencies, right? We already talked about, oh, left, electronegative, right? And there's this concept called shielding. So what's this mean? What is shielding in NMR? Shielding. So this is the basic idea of it. Think about this being a proton. This is a proton, right? And it's got some valence electrons around it, little electrons. So the essential idea is that we have a magnetic field. That's the yellow thing. It's a magnetic field, right? So there's an applied magnetic field. And when you got these electrons, there's kind of this circular motion. The electrons go in a circular motion and create an opposing field. Okay? So you have an applied field and an opposing field. And when you have the opposing field, it just opposes the applied field, and it kind of prevents the full effect of NMR, right? What would be a good name for this? It's shielding, right? It's shielding. These valence electrons are shielding the nuclei from the full effect of the magnetic field. Shielding. That's the word, shielding. Okay, that's shielding. What do you think happens if we have a chlorine somewhere nearby, a chlorine over here. Pretend we have a chlorine that sucks electrons towards it because it's electronegative, right? It's going to pull the electrons away towards the chlorine, right? And what's that going to be called? Somebody said less shielding, and that's exactly it. Less shielding or de-shielding. De-shielding is the word, right? You got shielding, but if you got a chlorine over here or a ketone or something, an electronegative thing, it's going to de-shield the proton. And where do protons come if they're de-shielded? Downfield or upfield? It's downfield, which is to the left. Downfield to the left. Yeah, you got it. Yeah, good. That's the basic idea. We'll see some more examples in a second. All right. Okay, so all types of protons have different amounts of shielding. The right side protons are highly shielded. The left side protons are de-shielded, right? Next to a chlorine, right? Cool. Left side is usually de-shielded. They all respond differently and appear at different places. So that's what's so wonderful about NMR, is each of the signals come at different places, ideally. And that's, you know, for the most case, we see each of the different types of protons come at different places on the spectrum. If everything came at the same place, it would be really boring and useless, right? This is why NMR spectrum contains so much useful information. The different types of protons appear at predictable places. Okay, it's very predictable. That's what's so cool about this. Okay, so let's talk about the concept of chemical shift. So chemical shift, in a nutshell, is the position on the x-axis. All right, 3 or 5 or 7 or 1, or right. That's all we mean by chemical shift. There's a little bit of background we have to talk about, but essentially it's just the x-axis position. Okay. All right. So first thing. Peaks are measured relative to TMS. TMS is tetramethylsilane. It's silicon with 4 methyls. Tetramethylsilane, okay? So it's a 0 point. TMS comes at 0, all right? When NMR was created, people said, well, we need a 0 point. So TMS was found to be like a good place to define 0 to be. Now, why is TMS so far to the right compared to everything else? It's because of the silicon. It's got a lot of electrons, right? And it's shielded. It's extremely shielded. All the methyls are extremely shielded, and that makes them go to the right. And so TMS, you know, is as far right as you can go, basically, right? We define it as 0. Okay, and then the shift is measured in hertz, right? And it's just and everything to the left of that is downfield, right? Okay. All right, so the thing about chemical shift is that there's a couple ways to measure it. Let's just go back here. There's a couple ways to measure it. Measuring it in hertz is possible, but it's not ideal because the hertz depends on the machine you got, the NMR, right? The spectrometer frequency. Remember how last lecture, the hertz depends with the Larmor equation on the spectrometer frequency, the magnet strength, right? Okay, so that's not ideal. We'd rather have this be a universal measure that's independent of the magnet and everything. And that's what we're gonna do, is we're gonna define the x-axis a little differently. This second though, it's hertz. It won't be hertz in a second, though. Okay, all right, so somebody said, why silicon and not another element? That's a good question. Somebody said that in the chat. Why silicon and not another element? Well, silicon is unique in that you can make bonds to carbon really easily, and this is a very convenient chemical. It's very, yeah, I don't know. That's historically why we use silicon. It could be, there's other things that could be used, but this is a very stable molecule. Yeah. Okay. All right, so recall from earlier, strong magnetic fields cause the instrument to operate at a higher frequency. So basically, the frequency is dependent on a constant related to the magnet strength, right? Different magnets, different frequencies. And this makes, if we use the x-axis and we define it in hertz, that's a problem because then every different NMR machine is going to have a different x-axis, right? We don't want that. We want a universal x-axis, and that's what we're going to have a way of doing that. Okay, so the shift depends on the spectrometer frequency. Very annoying. We don't want that. We don't want different machines to have different x-axes, right? So what we do is we normalize the chemical shifts to be independent of the spectrometer frequency. And we define something called chemical shift, which is also called delta. So delta chemical shift, same thing. All it is the shift in hertz divided by the spectrometer frequency, which is like it's like 300, 500 different numbers. And that's also called ppm, okay? This is super cool because it's universal. Every NMR in the universe has the same scale, basically, once you do this, all right? Okay, so the shift in ppm is universal in modern NMRs. The shift in ppm is universal in modern NMRs, okay? And that makes it just simplifies things. We like simple stuff. Okay, so if a chemical, so the ppm scale goes from 0 to maybe 12 or so. This is just showing it's about 7, but everything in organic chemistry is kind of like between 0 and like 12 or so. The meaning of a ppm, 1 ppm, does vary based on the spectrometer frequency. So on an old NMR machine, 60 megahertz, ppm means about 60 hertz. On a modern machine, it's actually more hertz, and that basically gives you more resolution. The meaning of this is that, like, if I buy a modern NMR for $500,000, I get better resolution. Like, the meaning of 1 ppm is that there's a lot more space in there and resolution. You can actually get better signal. That's the basic takeaway message. And of course, ppm is cool because we have a single scale that is universal worldwide. Everybody uses the ppm scale, okay? All right, so charts of chemical shifts. This is also in the syllabus. In the normal class, this would be on your exams. You guys have this on your quizzes. It's good to have this somewhere. It's also in the syllabus. So if you print out the syllabus, you have this. This is super cool. It's a simple chart that allows you to almost solve any NMR problem in terms of the location on this scale. Aliphatic basically means stuff like CHs, CH3s, CH2s with nothing around them. CH next to pi bond is really cool. So what's a pi bond? What kind of organic molecules? Functional groups have pi bonds. I don't know. Do you know any functional groups? Like ketone. Yeah, so we said ketone. A CH next to a ketone, where's it going to come? Between 2 and 3. That's pretty universal, okay? A CH, CH2, CH3 next to a ketone is kind of in this 2 to 3 range. What about a CH where C is next to an electronegative atom? That's between 3 and 4. Okay? Like what's some electronegative atoms? You know, like a chlorine, bromine, oxygen, haloalkanes, all that stuff. 3 to 4. Alkenes are between 4 and 6. Okay? Alkenes are between 4 and 6. Benzenes are between 6 and 9. Aldehyde, CHO, 9 and 10. Carboxylic acid between 10 and 12. Super, super cool. You don't have to memorize this, but have this somewhere nearby, or, you know, if you're on a tablet or computer, just, you know, make a copy of this, especially when you're learning this stuff. This chart's just going to help you out so much. Now, there's a little bit of exception here and there, and so this is a general guideline, but there will occasionally be a little bit of an exception. Like if I have multiple electronegative atoms, it might be a little further downfield. Multiple electronegative atoms, right? But anyway, this is a good start, right? Okay, you don't need to memorize it. I would try to remember the general order, but have it available. You know, it's an open note course. This is another one. I think this is a little more complicated, but it's basically says the same stuff. aliphatic. These are kind of next to pi bonds. Aromatic is a pi bond, right? A benzene, those are pi bonds, right? Nitrogens are also kind of in this around 2 to 3 range. Most electronegative atoms are kind of in this 3 to 4 range, maybe a little further than 4. OHs and NHs are a little weird and variable. They can be all over the place. So there's maybe a little bit of a broader range. We'll talk about those later, so don't worry too much about those right now. Alkenes, like I said, kind of 5, 6, maybe a little further. Benzene, 7 to 8. Aldehydes have their own little window. Carboxylic acids, 11 and 12. Okay, so should you be scared that there's overlap? Don't be scared about this. You know, we're going to be able to. This will be so amazingly useful in a second, and it doesn't really matter that sometimes things overlap. Remember, this chart is actually almost perfect. It defines almost every situation you're going to see, with a couple exceptions. But the exceptions are not a big deal. I don't know. You'll see what I mean when we get to these problems. Okay. Why does deshielding occur? We already kind of talked about that. Many reasons. We're going to talk about 2 situations, though. Why does deshielding occur? And that what happens when things are deshielded? They move to the left, right? Left. Okay, so the first one, like we already explained this, right? Chlorine, electronegative. CH. What happens to the electrons? Those electrons are shielding, right? The electrons are shielding, but if the electrons get pulled away, it's deshielded. Chlorine pulls the valence electrons away, and they're not shielding the proton anymore. Thus, the proton appears deshielded and it shifts to the left. This is a simple situation. We just explained it, right? This one, oh yeah, this is great. This shows a variety of electronegative atoms. So X, there's a definition of X, like a quantitative definition of X. So X is the electronegativity. And if we consider different electronegative atoms, well, there's different atoms with different electronegativities. Look at the effect of chemical shift. Silicon is very non-electronegative, right? And it's their 0 point, it's TMS. But as you start increasing electronegativity, what happens to the chemical shift? It keeps increasing and increasing and increasing and increasing. So it's like it varies with electronegativity, right? With like fluorine being a pretty extreme example. Fluorine's very electronegative, right? And it actually shifts it down to 4. I mean, it's pretty far down. The chlorine is like 3, bromine's around 2, etc. But fluorine's pretty extreme, okay? What if we have, let's compare, and I already mentioned this example. What if I say 1 chlorine versus 2 chlorines versus 3 chlorines, right? We have chloromethane, dichloromethane, or trichloromethane, or also called chloroform, right? What's the effect on the chemical shift? 3 to 5 to 7. So these go off that scale I showed earlier, and that's what I was saying. There's some exceptions. When you have 3 chlorines, yeah, that's going to have a huge effect. Okay, but the fact that there's exceptions to the chart doesn't mean, oh, the chart's bad. It's like, you know, we deal with the exceptions when we need to. Okay, the effect increases with a greater number of electronegative atoms, right? Of course. Why does chloroform come at 7 ppm? Because you have 3 chlorines on there, right? The 3 chlorines really suck the electrons away from the CH. Okay. Also, if this is considering a CH2 next to Br, a CH2 further from a Br, and a CH2 even further from a Br, you can see what's the effect on this CH2, the red one. It, you know, as you go further away from the bromine, the distance dissipates, right? The effect dissipates, right? So the bromine has an electronegative effect, right? And if the CH2Br is next to the bromine, it's at 3.3. this CH2 is a little further from the BR, so it still feels the effect, it's just a little further. My point is the effect depends on distance, right? So, or you could say that the effect can travel through a couple bonds. Like this CH2 actually feels the effect of that BR, right? A little bit, just a little bit. It's far away, but it feels it. Anions are shielded and cations are less shielded. Somebody said that. Well, let's not think about anions and cations right now. We're not going to see that much in NMR. But you could, that's probably true. It's probably true. I don't have a general answer this second on anions and cations. They could be a little different. All of these kind of molecules are just neutral organic molecules. Okay. All right. A couple examples. All right, now we're ready for examples. So this is tert-butyl methyl ether. Tert-butyl methyl ether. Integration is just shown with these numbers, 3 and 9. What do you think is the 3 and what's the 9? Oh, the 9's a tert-butyl group and the 3 is the methyl group, right? That's easy. Is the methyl where you'd expect it? It's the methyl. Why is it a 3? Maybe because it's next to a oxygen, right? And on this scale, that's totally right, right? See how it's a CH where the carbon is connected to an electronegative atom? Well, oxygen is an electronegative atom, right? So it totally makes sense that the CH3 would be around 3-ish, right? And then the 9, these 3 CH3s are not directly connected to the oxygen, right? They don't feel the effect of the oxygen very much, and that's why they're kind of around 1, okay? How about this crazy molecule? Okay, so how many different kinds of protons are there? Well, looking at the structure, it's pretty easy. I see 1. Now these 2 guys are the same, so that's 2. The 2 CH3s, right? They're identical. And then the CH2Cl is 3. So there's 3 kinds of protons, right? 3 kinds of protons. Now, the integration gives it away, right? 1 to 2 to 6. Well, what's the 1? What do you think? I don't know. Maybe it's the only CH in the molecule. What's the 2? I don't know. Maybe it's the only CH2 in the molecule. And the 6, I don't know. It's the 2 CH3s in the molecule, right? So the integration tells us, but what about the chemical shift? Does this make sense? The CH next to 2 chlorines, way downfield. Yeah, it makes sense because you have 2 chlorines, right? This chlorine is just a CH2 chlorine. That's between 3 and 4. That kind of follows what the chart says, so that makes sense. And then the 2 methyls, they don't really feel the effect of the chlorine very much. They're kind of around 1, right? We cool? Normally in a classroom, I can see smiley faces and frowny faces and figure out if we're smiley or frowny. But I see smiles. Okay, all right, good. So every now and then, throw in some smiles in the chats or frownies, and I can be like, figure out if you guys are happy or not. Okay, let's keep going. Why does deshielding occur? The second situation, why does aromatic come really far downfield? 7 to 8. Why does aromatic are kind of weird. Okay, now this chart's going to be, I see some half smileys and oh god. All right, I'm going to accept these as like everybody's kind of happy-ish. Okay, why aromatic are weird? Okay, they come around 7 to 8. Is that downfield? Yeah, it's kind of downfield. It's pretty far downfield. I see somebody said sp2. It's a little more crazy than sp2. The basic reason is this, and don't be too scared. It's a ring current effect. So think about it this way. We got an applied field. We have, right? We have a magnet. It is creating a circulating motion of the electrons. There's a bunch of electrons, right? You got a bunch, six electrons in the pi bonds, and they are circulating. The magnet causes the circulation of the electrons. Okay, And right in the middle of the benzene, there's kind of a, like if I was describing the effect of these electrons right in the middle of the benzene, would you say they're shielding the effect of the magnet, or are they de-shielding? Right in the middle, if that makes sense. Like, are these in the same direction or the opposing direction? In the middle. I mean, it looks like the arrow is going down and this arrow is going up. So you might say, if arrow is going down and this arrow is going up, is that opposing or agreeing with? One arrow is down, one arrow is up. You'd say opposing. That's correct. Somebody said opposing. It's totally opposing, right? And if it's opposing, you'd say, is it shielding or de-shielding? Opposing in this context. Opposing, is that shielding or de-shielding? You would say opposing is probably shielding, right? Right? You'd say that in the middle of the benzene, we have a opposing shielding effect, right? It's shielding, right? But the question is, in a benzene, are there any CHs in the middle? Or are the CHs on the inside or the outside? Look, they're on the outside, right? Okay, so there's no CHs in the middle. So if there were CHs in the middle, they would be shielded, right? And shielded is to the right or left? Because shielded, we said shielded, like TMS and stuff, right? Yeah, yeah. So if there were CHs in the middle of the benzene, and they're not, they'd be shielded. But what happens is this circulating motion continues around from the middle and comes around. And now the protons on the outside experience not a shielding effect, but what's the opposite of shielding? Opposite of shielding, de-shielding. That's exactly right. Okay, so the protons in the middle, but there's no, imagine protons in the middle. Imagine, oh, it's a weird benzene, there's protons in the middle. They would be shielded, right? But the protons on the outside, and those are de-shielded, okay? And de-shielded, is that to the left or right? De-shielded is to the left. And not only is it to the left, it's extremely to the left in this case, which is 7, right? 7 ppm. That is why a benzene has the protons really far to the left, 7 ppm, okay? Okay, this is gonna be super cool, super cool. When we talk about the aromatic chapter, we're gonna talk about some huge aromatic rings, bigger than benzene, right? Massive, 14 carbons, 14 carbon rings, all right? That have protons in the middle. They have protons in the middle. So it's kind of like this. Imagine this, but being huge, 14 carbons and protons in the middle. Are those expected to be shielded or de-shielded? Protons in the middle.
Shielded.
Those are expected to be shielded, and they will be shielded. They'll be so shielded, the ppm will be like -4. They're going to be to the right of TMS. They're going to be extremely shielded, right? And then the ones on the outside are actually extremely de-shielded, like 14 or 15 ppm. That's a weird molecule, but we'll see that in the aromatic chapter. All right. So that's kind of the basic idea. In benzene, though, it's really simple. Middle, there's no protons. The middle would be shielded, but there's no protons. But the field just continues around, and then the outside protons are de-shielded, and de-shielded so far that they go up to 7 ppm, okay? That's the basic idea. Do you need to know the theory of this? No, you don't. I'm not going to test you on this theory, okay? So don't worry about it. If this is a little confusing, don't worry about it, okay? But now you know, though, hopefully, maybe a little bit of, why does this work and why does benzene come at 7? Now you know. Here's an example. This is methylbenzene, also called toluene. I have my little chart up here just so you can check out the chart. It's kind of cool. Chart works in a lot of cases. Okay, so we have a proton, 5 protons and 3 protons, right? 5 and 3. We cool with that? What's the 5? What's the 3? The 5 is the benzene. The 3 is the methyl, right? Are the chemical shifts where we expect them? The benzene is at 7, right? We're smack dab in the middle of the benzene region. And what about this guy, the methyl? It's between 2 and 3. Is that in agreement with the chart? Between 2 and 3, is it? It's a CH next to a pi bond. Yep. Those CHs are next to a pi bond because these are all pi bonds, right? And there's a little bit of, a little bit of a pulling effect. A little bit of a pulling. The benzene causes a little bit of a pulling. But in general, yeah, anything next to a pi bond, 2 or 3. Okay? Kind of cool, huh? Smiley or frowny? Or nothing? Okay. All right, so that's benzene. It's not exactly benzene, it's methylbenzene. Okay? Okay, next lecture. Remember, it's a whole bunch of mini lectures. So next one, now we're on 3, I think. Okay, part 3, mini lecture number 3. Okay, this is a very small little mini topic, but we're just gonna kind of go through it. Recognizing equivalent protons in a structure. Okay, so in general, chemically equivalent protons have the same chemical shift. So protons that are all kind of on the same place, same environment, have the same chemical shift. That makes sense, right? But chemically non-equivalent protons will often have different chemical shifts. That makes sense too. That's what we've been showing, right? Okay. Thus, NMR easily tells the number of different types of protons, right? Makes sense. So, example, you tell me how many different kinds of protons we might expect. I'm choking to death. Let me have some coffee. How many different kinds of protons? It's a small number, but it's not one. Wait, I lost the chat. Where's the chat? I see 2, yeah, 2, exactly. You got the outer one and the inner one, that's 2, right? A and B, okay? 2 sets of non-equivalent protons. Which one's the downfield one, A or B? Downfield, downfield means to the left. And of course it's B, right? This is next to the chlorine, that's right. Okay, how many types of protons? Yeah. 3, yeah, of course, A, B, and C, right? Get it? Here's the downfield, probably C, right? Next to the BR. Scary. How many different kinds of protons? We got, let's see, 1, 2, 3. You might see a pattern developing as we go from the first to the third to the first, second, and third. But I don't know, it looks like, yeah, 4. The methyls, identical. And then we have a CH, a CH3, and the CH2Cl. That's 4, right? 1, 2, 3, 4. Do we directly see the ketone? Well, we don't directly see the ketone by proton NMR. The ketone itself is invisible. We have some cool ways to figure out that the ketone's there, and we'll get to those a little bit later. But yeah, 4. And I like how we label them, like A, B, C, and D. That's a useful trick. How many different kinds of protons? Okay, so this is a little weird because the benzene has some symmetry to it. But I think we have the left one, this one. The CH2, it's 2. Now with this kind of symmetrical environment, these are going to be identical, and these are going to be identical. And then you have this one. So I think it's going to be 1, 2, 3, 4, 5. So it should be 5 actually. Because these 2 CHs on the benzene are different than these 2 CHs, right? These 2 are away from the ketone. These 2 are closer to the ketone, right? So they're a little different. 5. A, B, C, C, D, D, and E, right? Okay. Ooh, scary,
I have a question.
scary. So now we got another benzene.
Professor, I have a question.
Symmetrical. Is it a question?
For the one with the ketone, the CH2, I thought that if there was a chiral center, we count each individual hydrogen.
That is true, but there's no chiral there. So that is true. Somebody said if you have a CH2 next to a chiral center, that the two CHs would be independent. We're not going to really see that in this course just because we're not going that far into NMR theory. But furthermore, this isn't chiral.
No, I was talking about the one with the the third one.
That's actually, that's a good point. The third one, we actually do have this issue, but we're probably going to kind of not deal with that right now.
Okay.
For the most part, that is technically correct. That the protons on carbon C here can be might be different based on the chiral center next door. Let's kind of ignore that for now. But that is in advanced NMR theory, yes, we definitely have that issue. We're gonna not spend any time on that right now.
Okay, thank you.
Okay, cool. How about this one? So this is a non-symmetrical benzene, and so how many? So you got the CH3, that's one. But each of the aromatic CHs are actually different because now there's not symmetry. The benzene's not symmetrical. So I think it's going to be 1, 2, 3, 4, 5, 6. So the CH3 is the sixth one. Each of the aromatic are different though, okay? So A, B, C, D, E, F. So 6 sets of protons. Okay, so each of these CHs experience slightly different environments, right? Of course, A is a CH3. E of course, is in between the methyl and the OCH3. But B, C, and D all are slightly different, right? B is next to a methyl. C is just in the middle of nowhere. D is next to the O-methoxy, right? Or the CH3, right? So that's why each of these are expected to be independent CHs. Okay, cool. All right, now this is just a very minor weird phenomena. Don't worry too much about this, but cyclohexane, right? You know cyclohexane. It's got what are these kind of protons? We got axial and equatorial, right? Axial and they're kind of just flipping back and forth, right? Now, it's interesting that you might think, well, they're just kind of flipping back and forth. You got a bunch of CH2s, they're chairs, that you might just see a single peak, right? For all of the CHs, right? It's kind of a boring molecule. Interestingly, at 25 degrees Celsius, room temp, and you take an NMR of this, it's a single peak, okay? Now, that is because these are flipping very, very rapidly back and forth, back and forth, back and forth. And there's like no difference between the axial and the equatorial signals. If you cool this down, you can do some interesting things when you cool molecules down. At negative 90 degrees, you actually slow down the flipping. So it's not flipping as fast as possible. And we can actually see the individual conformations. So I can see the axial and I can see the equatorial. So I can actually see the different kinds of protons in a cyclohexane. That's a very rare, kind of weird case, but I just kind of mentioned that. Okay. All right, and in general, cyclohexanes are a little weird. So we're not gonna see them that often in our NMR discussion. We have a lot to talk about that's very straightforward. But cyclic molecules can be kind of weird. Okay. Okay, so, all right, so what have we talked about so far? We talked about integration. What was integration? It was the area under the curve, right? Number of protons. We also talked about chemical shift. What was chemical shift in a nutshell? It's kind of the chemical environment around the protons, right? Is it next to chlorine? Is it next to a benzene? Is it the benzene, etc.? There's a third thing we got to talk about, and that's called spin-spin splitting. It's like the third major thing, all right? So we got integration, we got chemical shift. Now we're going to talk about spin-spin splitting, all right? So we already saw this a bit, and we just didn't talk about it. A group of hydrogens might appear as a multiplet rather than a single peak. We already saw this a bit, like a triplet or a doublet. It's like you see like a couple of mini peaks come out of a signal, right? The multiplets are named as follows. So we have a singlet. Singlet's a single peak. We have doublet. We have a triplet, quartet, quintet, sextet, septet, octet, and nonet. Of course, these all kind of make sense. It's just the number of peaks, right? All right. This happens because of interaction with neighboring hydrogens, and the name is called spin-spin splitting. All right. So we'll see what that means. What that means. It's going to be something about like, yeah, interaction between like a CH2 and like a neighboring CH3, you know, that kind of thing. All right. That's the basic idea. Let's see what we mean by this. All right, so this is a really ugly looking NMR of this molecule. CH with 2 chlorines and then CH2 with a chlorine, all right? So first question, which one of these is the downfield one? Is it gonna be the left to the CH or the CH2? It's gonna be downfield to the left. And it's probably the CH, right? Why is the CH downfield? Because it's got 2 chlorines, right? And it's coming pretty far downfield. It's like 6 ppm almost, right? Okay, and of course the integrations make sense. One's a CH, one's a CH2. Oh, that all makes sense. Well, what's the thing that doesn't make sense? The multiplets. And this is going to be really cool, all right? So the multiplets are due to this thing called spin-spin splitting, and they're predicted by something called the n+1 rule. The n+1 rule. So what is this n+1 rule? Here it is in a nutshell. Okay, the CH. How many neighbors does a CH have? Like neighboring CHs. Yeah, it's a CH itself, but how many neighboring CHs are there? How many CHs are there next door? There's 2, right? The CH has 2 neighbors, right? Okay. So the rule is going to be called the n+1 rule. I don't know. 2 neighbors plus 1. That's it. That's the rule. The CH has 2 neighbors. The CH has 2 neighbors, right? The CH has 2 neighbors. 2 plus 1 is 3, and that's what we see here. Oh, it's a triplet, okay? So the CH is a triplet. Why is the CH a triplet? Because there are 2 neighbors. 2 plus 1 is 3, right? What about the CH2? How many neighbors does this CH2 have? And the CH2 has 1 neighbor, right? What's 1 plus 1? 1 plus 1 is, of course, 2. And so what's the appearance of the CH2? Oh, it's a doublet. Because the splitting, this whole idea of the splitting is number of neighbors. Number of neighbors plus 1. That's all it is. Seems a little crazy, but it's not that crazy. It's always a little crazy when we first learn it, okay? All right, so the CH is a triplet because there's 2 neighbors. 2 plus 1 is 3. And the CH2 is a doublet because it has 1 neighbor. 1 plus 1 is 2, doublet, okay? All right, let's keep going. I'll explain why that is. There's a really cool theoretical reason for why we actually see the n+1 rule, okay? All right, so yeah, where do they come from? Interactions with neighbors. We just said that, right? So yeah, the CH is split by the 2 CHs next door, and the CH2 is split by the 1 CH next door to it. Okay, so this CH is split by its 2 neighbors, and we're going to explain how that actually works in a second. All right? And this CH2 is split by its neighbor. It's 1 neighbor, and that becomes a doublet. So that's how the CH is a triplet and the CH2 is a doublet, okay? And the different multiplets we see are singlet, doublet, triplet, quartet, quintet, sextet, septet, octet, and nonet. And that all, like, These bottom ones are always if you have a ton of neighbors around your CH or whatever, okay? Okay, couple exceptions. If you got two like CHs and they have X's and Y's, and the X's and Y's are the same, like they're basically identical, well, then you don't have splitting. The splitting doesn't occur. You need to have like an asymmetric molecule, okay? Like difference on one side or the other. Same as if you have two CH2s with an X and Y on both sides. And if the X and Y are the same, there's no splitting. So one of these has got to be different, okay? Protons in the same group usually do not split each other. So it's usually a neighboring group thing, right? So these, like a CH3, it's not like the CHs split each other. The CH3 is just, it's a CH3, right? It's just a single signal. Same with a pair of CHs, like in a CH2. There's going to be a couple exceptions to this, but this is a pretty general rule for now. Okay, all right. What if I just have a long chain, a bunch of methyls, or CH2s and a CH3? The answer is yes, you will see the n+1 rule will work, like, right? So like this left one will be a triplet, right? Because it's got two neighbors. What about this one? Think about this one right here, this CH2. How many neighbors does this CH2 have? There's two on the left, two on the right, 4, right? 4 plus 1 is 5. We call it pentet, right? That's going to be a pentet, okay? Another pentet. This one, 5 neighbors. 5 neighbors. 5 plus 1, 6. So it's a sextet. That's what it is, 6 for sextet, right? Also, like a methyl cyclohexane. These kind of things, the n+1 rule works. Alkenes are a little funny. They actually kind of do work depending on the alkene. So this is a little misleading. We'll show alkenes in a bit. Don't worry about this. And then also like on a benzene, depending on the benzene, actually sometimes it does work. So I would say these are a little misleading. We're going to see a lot of examples. So just hang on a little bit, all right? And lots of examples of where it works. Okay, so it's common splitting patterns. Common splitting patterns. All right, what if I got a pair of CHs? Just a pair of CHs with X and Y, some X and Y, and they're different. What are they going to be? Oh, a doublet and a doublet. Makes sense, right? One neighbor, one neighbor. Each has one neighbor. 1 plus 1 is 2. Doublet, doublet, right? What about a CH2 next to a CH? The CH2 next to a CH. Well, the CH2 has how many neighbors? 1, right? So the CH2 is going to be a doublet because there's one neighbor. What about the CH? How many neighbors does the CH have? It's got 2 neighbors, right? The CH has 2 neighbors, 2 plus 1. Ah, it's a triplet, okay? It's the number of neighbors plus 1. That's the rule. What about 2 CH2s? And then some kind of X and Y groups that are different. One's got 2 neighbors, the other's got 2 neighbors. They're both triplets, right? So triplet and a triplet. All right. What about the CH next to a CH3? The CH, how many neighbors does that CH have? The CH has 3 neighbors. So the CH is, what's this called? Somebody say the word. So something tet. Something tet.
A quartet.
Quartet, yeah. Whereas the CH3 has how many neighbors? The CH3 has how many neighbors? It's got 1 neighbor, 1 plus 1 is 2. It's a doublet, right? Make sense? Ethyl is an ethyl group. CH2, CH3. We're going to see this a million times. Probably more than anything else we're going to see in this course. Ethyl group. We're going to see so many ethyl groups, you're going to be sick of ethyl groups. Okay, ethyl group is a CH2 and a CH3. The CH2 has how many neighbors? The CH2 has 3 neighbors, right? 3 plus 1, it's a quartet. The CH3 has how many neighbors?
Two.
2. CH3 has 2 neighbors. It's a triplet. Get it? It's all just number of neighbors plus 1. What's this called? Anybody know? It's something propyl. Something propyl. I word.
Isopropyl?
Isopropyl. Isopropyl. Why are we iso? Somebody said a question. I don't understand. Why are we iso?
Sorry, that was me. For
Okay.
the one on the left in the middle,
This one?
yes, why are we not counting the methyls?
The methyls?
Yeah, I see,
We're all we're talking about is really just the CH2 and the CH. Now there's other stuff, but we're trying to just focus on
oh, I see.
two things.
Okay,
Yeah.
okay, thank you.
Okay. All right. This is an isopropyl group, right? Okay. Now the CH of the isopropyl has how many neighbors?
6.
6.
6, right? 3 plus 3 is 6, right? What's 6 plus 1? 7. The name of that is, somebody say it, something tet.
Septet?
Septet. And that's how many peaks? 1, 2, 3, 4, 5, 6, 7. So that's a septet, right? And then this doublet's going to be really big because there's 6 protons. It's 2 methyls, right? Of course, it's a doublet. Why is it a doublet? Because there's a single proton next door, right? All right, cool. That's the bunch of cool examples of the n+1 rule, and we call these common splitting patterns. It's like we see a lot of different things, and these are a couple examples. All right, let's see some more. Benzenes. Para-disubstituted. So para-disubstituted means you got a benzene and you got X and Y are on the opposite sides of the benzene. We're assuming X is different than Y. So it's like maybe a chlorine and a nitro or methyl or something like that. What do you expect? A pair of doublets. Why do we see a pair of doublets? The answer is you have 2 protons like these 2 protons, and those are different than these 2 protons, right? Okay. But each of the pair of protons, it's like this pair of protons, or like this, this CH is identical to this one. You count the neighbors. There's only basically one neighbor, right? Like each of these has one neighbor, which is like the next door proton, right? So para-disubstituted is going to be a pair of doublets. This is super cool because this is super cool because we can identify if it's a para, and we also have meta and ortho. Those are the other benzenes, disubstituted benzenes, and we can identify them and we say, oh, pair of doublets is a para-disubstituted benzene. Okay, this is an example. Chloro-nitro. So we have a chloro on one side, nitro on the other. This is all in the benzene region, that kind of 7-8-ish region, right? Pair of doublets. Pair of doublets. It's para, okay? It's pair of doublets. When you see the pair of doublets, you say, must be para-disubstituted, okay? Ortho and meta are the other patterns. They have their own characteristic splitting patterns. So the chemical shifts will vary. Let's not worry about the chemical shifts. Let's focus on the splitting right now. Don't worry about the chemical shift. Chemical shift is like where the peaks are. We care about the splitting right now. The question was, so basically it depends on the carbons that are connected to the specific substituents. It's just really the neighboring protons and how many neighboring protons there are. Let's see one of these. This is called meta. Okay, so first of all, so this is para. Para is opposite. You got the 2 things are on the opposite sides. This is called meta, M-E-T-A. It's when you got 2 things that are separated by like 1 CH or whatever. Okay. And what is the splitting pattern? It looks like I got a singlet, 2 doublets, and a triplet. A singlet, 2 doublets, and a triplet. Regardless of the order of them, the big thing is Okay, well, I got a singlet. Okay, I got 2 doublets. Okay, I got a triplet. That is what you would expect for a meta-disubstituted benzene. Where's the singlet? Here's the singlet. Which of these CHs has no protons next door? Say like bottom left or bottom right, or there's this one. It's hard to talk right now, but yeah, it's this one. This is a singlet. Why is it a singlet? Because there's no neighbors. 0 plus 1 is 1. It's singlet, right? Then you got these 2 guys. How many neighbors do these 2 CHs have? Like this CH. This CH alone. Just how many neighbors? 1, right? 1 plus 1 is a doublet. Okay. You got this one. How many neighbors does this one have?
1.
1. Okay. Singlet, 2 doublets. And what about this one? This one, how many neighbors does it have?
2,
Got 1 up here, 1 down there, 2. 2 plus 1
3,
is a triplet. So now we know how to identify para. Let's go back. Para is para-doublets. Now we know meta. Meta is a singlet, 2 doublets, and a triplet. Somebody asked, would there ever be peaks in between the para? Probably not. Para, if it's an aromatic and you just have 2 things on it, there's nothing going to be like in between. I mean, it's like you got one peak, you got the other peak. That's it. Okay. Okay, we got meta. We got our meta, yeah. What's the other one? It's ortho. And this is ortho. Ortho means you got 2 things that are next door to each other. 2 things next door to each other, right? And what is the splitting for ortho? Okay, well, I got, what are these guys going to be? The top and the bottom. Of course, how many neighbors are on the top? How many neighbors on the bottom? Neighbors, so there's 1 neighbor each, right? 1 neighbor each. So what's the splitting of the top and the bottom? They're both going to be
doublet.
doublets. That's right. Doublet, doublet, right? What about these guys? These both have 1 CH on one side, 1 CH on the other. 2 neighbors. 2 plus 1 is
Triplet.
triplet. So what do we have? We end up with basically 2 doublets, 2 triplets. We don't, the exact order doesn't matter. It doesn't matter if it's a doublet, triplet, or doublet, doublet, triplet, or triplet, triplet, doublet, doublet. That's, we don't care about that right now. The main thing is I want to be able to distinguish ortho from meta from para. Okay? And what do we have if it's para? Go back to para. Para is para-doublets. Right? What do we have with meta? Singlet, 2 doublets, and a triplet. Singlet, 2 doublets, and a triplet. And what about ortho? 2 doublets, 2 triplets. That is super cool. We can pretty rapidly figure out for a benzene, is it going to be ortho, meta, or para by the signals we got, all right? Super cool. Okay, let's see some examples. Just random examples with splitting. Bromoethane, really boring. Really boring. This is we talked about ethyl, right? Quartet, triplet. Well, there's your quartet, there's your triplet. Okay. Who is the downfield one? 3-ish is probably the one next to the bromine, right? That's chemical shift. What are the 3 things we care about? The integration, the chemical shift, and the splitting. So all of those things make sense. I don't think I tell you the integration though, but the integration should be 2 to 3, right? Yeah, it's 2 to 3. What about nitro, I don't know the name of this. 2-nitropropane. Okay, well, it looks like we have a crazy, it's an isopropyl group, right? Crazy multiplet in the middle, right here, and we got this big doublet there, right? This one is probably a septet because it's got 6 neighbors. 6 plus 1, 7. You count really carefully, you probably see 7 peaks. 1, 2, 3, 4, 5, 6, 7. Yep. 7 peaks. The side peaks are a little deep in there. That's fine. What about the big doublet? The big doublet. The big doublet is the pair of CH3s. Somebody said, what is the O spike? Zero. That's the TMS. Remember TMS? Is our 0 point. It's a calibrant. We always add a drop of TMS, or it's in the solvent already. This little guy at 7.2 is the NMR solvent. I'm not going to really talk about that, but it's probably chloroform, and you might see a little peak at 7.2 sometimes. But yeah, major stuff we care about, the septet and the doublet, all right? 2-nitropropane. Acetaldehyde. This is a 2-carbon aldehyde. All right, so there's 0, we got our TMS. Big doublet at 2. Big doublet at 2, who's that? It's a CH3, right? Because why is it a doublet? Because there's one neighbor, the aldehyde, right? This, and then we have the aldehyde. Then you got the aldehyde peak, which is, where did aldehydes come? If you look at the chart, it's way down. It's about 9 or 10. It's actually off the scale. So this little peak is actually further down than it's around 9-ish, 9, 10-ish. And it's what is it? It's a quartet. Why is this CH a quartet? Because how many neighbors does it have? How many neighbors? Oh, 3. 3 neighbors. 3 plus 1, it's a quartet. See? Makes sense, right? That just kind of shows what this splitting looks like. Doublet, quartet, whatever. Okay? Interesting little tidbit. The intensities follow Pascal's triangle, which is a little kind of, you might have seen this in a math class maybe. It's just kind of the intensities of the peaks follow this sort of triangle. I don't know where Pascal's triangle originated. It's somebody named Pascal. But basically, like, it's a little triangle, and like singlet's the top, and it's 1. Each little leg is the sum of its parents, I guess. So like a doublet is a 1 and 1. So the intensities are 1 and 1. A triplet, like the 2 is the sum of the parents. The sum of the parents, right? And then the legs are 1. So this just shows kind of the intensities. It's not that big of a deal, but you do see this for the intensities. Like a quartet is 1 to 3 to 3 to 1 in terms of the line intensities. Okay, we'll actually see why this is the case in a second. We talk about the theory of splitting a little bit more. The origin. So why does it happen? Why does it happen? It's kind of a weird thing. And you don't have to know the theory, but it's kind of fun and it makes sense actually too. But why does it happen? All right, so I'm going to talk about protein HA. It splits into a doublet due to the spin of its neighbors. So let's talk about HA. HA, of course, HA is a doublet, right? HA. And so the reason that HA is a doublet, is because when I consider HA, its neighbors, which is a single CH, right, can either be aligned with the magnetic field or disaligned. And that actually causes a little bit of a shift to the left and a little bit of a shift to the right of the signal. That is why HA gets split into a doublet. So HA is a doublet, right? So half of the CHs are either aligned with the magnetic field or half are opposed to the magnetic field during the experiment. And basically that's why it's a doublet, all right? Now let's see. Okay, a CH next to a CH, like this CH, same exact thing. So this CH sees the other CH, right? 2 CHs, they're both be doublets, right? They're both doublets. So this CH, when this CH sees the other CH, there's gonna you're gonna have kind of a aligned state and a disaligned state, and that makes a doublet. The other CH looks back, it's like, I see, I'm a doublet, you're a doublet, we're both doublets, right? The other CH looks back and it says, oh, aligned and disaligned. What's the net effect? A pair of doublets, right? That's not that crazy. It's gonna be kind of fun when we get to the other ones, like triplets and quartets. Okay, how about this one? this CH sees a CH2 next door, right? CH sees a CH2. When we think about the two CHs, they can either be aligned, 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 disaligned, or disaligned, aligned. And that's the middle leg. Or they can be disaligned, disaligned. There's basically 4 states of the neighboring CH2, right? Aligned, 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 disaligned, disaligned, aligned, or disaligned, disaligned. And that is why the CH, when it sees that CH2, gets split into a triplet. Kind of weird, but that's the theory. It's pretty accepted. What do you think this CH2 is going to do when it looks back? Well, it just sees a CH, so it's got aligned, disaligned, right? Kind of cool. How about a CH2 next to a CH3? So the CH2 sees a CH3 next door, 3 protons, right? And there's four states: aligned, 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 disaligned, aligned, aligned. That's kind of like the second peak. Aligned, disaligned, aligned, 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 disaligned, right? That's all this second leg. What about the third leg? That's now aligned, disaligned, 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 aligned, disaligned, or disaligned, disaligned, aligned. That's the third leg. And then we have the fourth leg, which is disaligned, disaligned, disaligned. And so that is why the CH2 gets split into a quartet. There's 3 neighbors, 3 plus 1, quartet, right? All right. If this doesn't make sense, it's not a big deal, so don't worry about it. The big thing is know the n plus 1 rule. You got to know the n plus 1 rule. But that is why this CH2 gets split into a quartet. What does the CH3 do when it looks back? Well, it looks back at the CH2. It's like, well, I'm going to be a triplet because P can be aligned, 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 disaligned, disaligned, aligned, or disaligned, disaligned. So that is the theoretical reason for why this CH2 becomes a quartet, and this CH3 becomes a triplet. A little weird. I don't know if you've ever seen weird things you've probably seen weird things before, but this is one of those weird things. You don't have to really understand or reproduce this like in quizzes and stuff, so don't worry about it. But now you know. Now you know why these things are split. We're going to wrap up in a second. There was an error. The error is corrected, so I think the red thing is actually an error. There's no more error. Used to be a little error in these arrows, but now they're all fixed. I think this is a great stopping point. I'll hang out for a bit, and I'll save the video and post it. I'll probably post it tomorrow. I have office hours tomorrow at 10:30, so I'll be here if you guys want to talk more. I'm always happy to talk a little bit after class, so hopefully it was fun. There's going to be some more cool stuff. The grand finale is going to be when I give you an NMR spectrum. You can figure out the structure, and we'll have some practice. I'm going to teach you how to do it, and it's going to be the coolest thing in the world. All right.
Thank you. Have a good
Thank you.
night.
Thank you.
I have a question.
Yeah.
When will you be posting your first quiz?
Okay, the first quiz is probably going to be posted on Tuesday. It's not going to have anything to do with NMR. It's going to be, hey, do a Wikipedia search and draw a structure. Just the practice of the submission process. So don't worry about it. You don't have to worry about right now. Just follow the NMR lectures. Did you get the email I sent? Because everybody got their own little URL. Hopefully you got it.
Yeah, I have it, and
So perfect. Yeah. So right now, don't worry about the quizzes. It's try to keep track of the NMR. Maybe read the NMR chapter a bit. But none of the current stuff is really quizzable quite yet. So just follow along. Have fun.
cool. Thank you.
All right. Thank you. Any more thank yous? Any more questions? I think we're wrapping up. All right. We cool? Have a wonderful night, guys.
Thank you, Professor.
Bye.